Section: Introduction. In this section, we focus on how we identify missed code size optimization opportunities in compilers using large language models, LLMs. We begin with a simple piece of code and iteratively instruct the LLM to modify it by randomly selecting from a list of mutation instructions. After each change, we compile the modified code and apply various differential testing strategies to spot any suspicious compiler behavior. To reduce false positives, we utilize both static and dynamic analyses, and we report any concerning compilation results to the user. For instance, after 5 mutations, our system detected a 36% increase in code size between 2 versions of the GCC compiler. Our approach consists of 2 main stages: mutating the code and employing differential testing strategies to uncover potential missed optimization bugs. We will explain each stage in detail, along with methods for identifying false positives and recognizing duplicate issues. When it comes to mutating code with LLMs, traditional methods for generating compiler test cases often involve defining a grammar for the programming language and sampling from it, which can be complex and lengthy. For example, C. Smith, a well-known tool, has over 40,000 lines of code. We take a different route by sacrificing the strict correctness of grammar-based generation, allowing us to use a simpler engine for code generation. We start with a basic code snippet and leverage an LLM to gradually increase its complexity. While LLMs can make syntactic and semantic errors, we address this challenge in 2 ways. First, since we are looking for missed optimization opportunities, we can work with a broader range of programs than typical functional tests. Second, we apply heuristics and analyses to help identify false positives. Section Summary. In this section, we describe our novel approach to identifying missed code size optimization opportunities in compilers using large language models, LLMs, to iteratively mutate seed code and apply differential testing strategies. Our methodology simplifies traditional test case generation by leveraging LLMs, allowing us to detect potential optimization bugs with minimal code and effort, ultimately identifying 24 bugs across multiple programming languages. Section: Seed Program. In this section, we begin with a seed program, similar to previous mutation-based testing methods. Our seed programs can be quite simple, as we accumulate mutations iteratively. At each step of our testing process, we create a prompt that directs the model to mutate the code by randomly selecting from a list of predefined instructions. We combine the instruction with the current code state into a prompt, which we then provide to a readily available large language model, LLM. In our work, we utilize the Llama 3.1 models, which have been pre-trained and fine-tuned on extensive data, with a knowledge cutoff in December 2023. For any late added language features, a more recently trained LLM would be necessary. We sample uniformly from a list of mutation instructions that we have organized into 4 main categories. 1. Control flow modifications. We ask the model to introduce new control flow elements, such as loops or conditional statements, and specify whether these should be top-level or nested structures. 2. Aggregate mutations. We instruct the model to add code that includes aggregate structures like arrays, unions, structures, and classes. In languages that do not support unions, we substitute them with enumerations. 3. Pointer code. We direct the model to include pointers to variables defined in the code. 4. Mutation of existing conditionals. If there are existing loops or conditional statements, we ask the model to complicate them without altering their meaning. For instance, changing a condition from if x equals 10 inches to if x is greater than or equal to 10 and less than or equal to 10. Our mutation instructions can be categorized as either dead code or live code, where dead code refers to changes that do not affect the program's execution. We designed these instructions to cover a range of program transformations, but they are not exhaustive and can be tailored for specific domains if necessary. Next, we outline 4 strategies for differential testing to uncover missed optimization opportunities. Once we select a strategy, we maintain it throughout the iterative mutation testing session. 1. Dead code differential testing. This strategy relies on the premise that adding dead code to our initial seed code, which evaluates to a constant, should not change the program's semantics. We disable all mutation instructions except those related to dead code. If the generated code changes, it indicates that the compiler failed to recognize the code as dead, which is a concern. 2. Optimization pipeline differential testing. Here, we leverage the idea that some optimization pipelines prioritize minimizing code size, potentially at the cost of performance. We compare code generated by the same compiler using different optimization settings and flag any significant size discrepancies, using a sensitivity threshold of 5%. 3. Single compiler differential testing. This strategy involves comparing code generated by different versions of the same compiler to identify size optimization improvements or regressions. If we observe a size regression, we flag it as a potential issue. 4. Multi-compiler differential testing. In this basic approach, we compare code generated by multiple compilers. If the sizes differ significantly, we flag the larger size as a potential indication that the compiler may have missed an optimization found by another compiler, using a threshold of 10% to determine significance. Section Summary. In this section, we describe our iterative mutation-based testing approach that begins with a simple seed program and utilizes a large language model, LLM, to generate code mutations based on predetermined instructions. We also outline 4 differential testing strategies to identify missed optimization opportunities, including dead code testing, optimization pipeline comparisons, single compiler version checks, and multi-compiler comparisons, each designed to detect potential issues in code generation and optimization. Section: Detecting false positives. In this section, we discuss how we detect false positives in our code generation process. We recognize that using a large language model, LLM, for coding can lead to bad examples, and while we can't completely eliminate incorrect code, we have found effective ways to minimize this risk through heuristics and validation tools. So far, we haven't encountered any undetected false positives using our 3 main techniques. First, we focus on dead code detection. When we ask the LLM to add dead code, we can't be sure it will follow our instructions, so we need a method to confirm that the code only contains dead code. Although the problem is generally undecidable, we use a proxy metric. By controlling the function signature of the mutated code, we can compile it into an executable program that includes a main method. We run this program with coverage instrumentation and compare the counter values to ensure they match. If the LLM alters the function signature, the compilation fails, and we start over. We acknowledge some limitations, such as unreliable debug info mapping, which can lead to false positives or negatives, but we find this method effective for our needs. Next, we implement sanitization. Every generated test case is compiled with sanitizers to catch potential memory violations and undefined behavior. For C, C++, we use UB-SAN and ASAN from LLVM. To further reduce false positives, we run examples through CompSert in interpreter mode to identify undefined behavior. Our experiments show that these sanitization steps reject less than 10% of candidates. We also use a static heuristic called monotonically increasing size, which is the easiest to verify. This method has a higher rate of false negatives. The idea is that compilers may label some code as unreachable and remove it, especially in cases of undefined behavior. Since our mutation testing adds complexity incrementally, the optimizer tends to remove code rather than add it, allowing us to use code size as a proxy for complexity. To detect duplicates, we employ 2 techniques. First, we conduct release screening by compiling with various publicly available compiler versions. If the versions where bugs appear overlap but are not identical, it suggests different bugs. Second, we use commit screening and bisection for regressions, identifying the first commit that introduced a violation. If this commit differs for 2 programs, it likely indicates 2 separate bugs. In the next part, we evaluate our iterative mutation testing approach for finding missed optimization opportunities in C, C++ compilers. For our experiments, we ran each of the 4 differential testing strategies for 8 hours using Llama 3.1 on server-grade GPUs, testing 2 configurations, 70 billion and 405 billion parameters. Overall, we evaluated 8 unique configurations, totaling 64 compute hours. Each configuration underwent a single-threaded test loop, stopping after 10 mutations if no violations were found, and repeating until the time was exhausted. Our results show that the 70 billion model produced significantly more programs than the 405 billion model. The compilable subset, which did not abort due to compiler errors, showed that the 405 billion model had slightly fewer compilation errors, with an average of 96.45% successfully compilable code across both models. The larger model was more effective at finding bugs, indicated by a higher violation rate, but it was also more expensive in terms of inference time. The 70 billion model, while less efficient, generated more violations in the same time frame due to its quicker inference. We also experimented with an 8 billion parameter model, but it frequently introduced errors, making it impractical for our needs. Section Summary. In this section, we discuss our methods for detecting false positives in code generated by a large language model, LLM, employing techniques such as dead code detection, sanitization, and duplicate detection to ensure the reliability of our iterative mutation testing approach. Our experiments demonstrate that while the larger LLM model is more effective at finding bugs, the smaller model generates a higher total number of violations due to its faster inference time. Section: Discovered bugs. In this section, we discovered and reported 24 bugs during the development of our approach, with a total testing time of about 1 week. We present a representative sample of these bugs. First, we found 5 bugs through dead code differential testing, where compilers failed to remove dead code. For instance, in GCC bug 116753, when we compiled certain code with the optimization setting for size, the compiler could simplify a loop to a constant. However, adding 2 dead conditions prevented this optimization, indicating a regression in value range analysis compared to an older version of GCC. In LLVM bug 112080, the constraint elimination pass could not identify a dead inner loop, but after we reported it, the LLVM developer provided a patch that successfully fixed the issue, yielding positive results in real-world benchmarks. Next, we reported 4 bugs related to optimization pipeline differential testing, where some optimization pipelines produced larger binaries than those aimed at runtime performance. For example, in LLVM bug 111571, code optimized with a high-level optimization setting was reduced to a constant, while a size-focused setting failed to optimize it, resulting in larger code. Similarly, in GCC bug 117033, we observed that the size-focused optimization generated larger code than a different optimization setting, due to inconsistencies in handling loop headers. We also identified 12 code size regression bugs through single compiler differential testing against older versions of the same compiler. In GCC bug 117123, we found that the current version generated larger code than an older one, traced back to a new optimization pass. The developers confirmed that this pass revealed a deficiency in another optimization step, which they subsequently fixed. In GCC bug 117128, we noted that the current version produced larger code than GCC 14 due to changes in the loop invariant code motion pass, although the real issue was related to register allocation that didn't occur in the older version. Lastly, we reported 3 missed optimization bugs through multi-compiler differential testing. In GCC bug 116868, we found that GCC could not prove a function returned a constant vector, while Clang could, due to different assumptions about memory allocation. GCC has since fixed this issue. We also encountered cases where our iterative test mutation sessions failed because the generated code did not compile, averaging about 3.55% of the time. In these instances, we reverted to the original code and restarted testing. We noticed that the model sometimes misinterpreted dead code, treating it as code that does nothing. We used dynamic instruction counts to filter out these invalid test cases. Section Summary. In this section, we report the discovery of 24 bugs during our testing of compilers, including issues with dead code elimination and optimization regressions in GCC and LLVM. We also highlight challenges faced in our LLM code mutation testing, where a notable percentage of generated code fails to compile or misinterprets dead code. Section. Extending to other languages. In this section, we discuss how our technique can be easily adapted to other languages since it utilizes a standard large language model, LLM, and automatic validation tools. We can simply change the prompt and the target compiler to extend our approach. To evaluate this adaptability, we converted our 150-line Python script for testing C and C++ compilers to work with Rust and Swift. The changes required for each language are minimal. We only need to adjust the compiler commands and the initial seed program as outlined in our previous section. We selected Rust and Swift because they are relatively new and lack robust infrastructure for generating random test cases. For our experimental setup, we modified the system to support Rust and Swift by updating the language in the LLM prompt and the compiler commands. We then executed a single-threaded testing loop for 1 hour for each language. In our results, we found 1 bug in Swift and 4 bugs in Rust during just 1 hour of automated testing. For Rust bug 130,421, the code produced a fully vectorized loop that could be simplified. The compiler assumed the loop was fully unrolled to determine that the sum of values was constant, but it was only partially unrolled and vectorized, resulting in larger code and slower performance. Swift bug 76,535 revealed an issue in Swift's compiler when using specific optimization pipelines. The compiler failed to recognize that a nested while loop was unnecessary, and removing it simplified the loop. This could be addressed in Swift if the intermediate language passes included a mechanism to analyze and eliminate dead computations. Rust bug 132,888 showed that code compiled with the Rust nightly compiler was larger than when compiled with Rust version 1.81.0, due to the backend choosing a different instruction sequence that increased overall code size. Rust bug 132,890 involved a simple array iteration that resulted in a larger binary when compiled with Rust nightly compared to version 1.73.0, again due to suboptimal instruction sequences generated by the compiler backend. In terms of related work, automatic test case generation for compilers is a well-established method for validation, often involving complex random program generators. Our approach differs by using mutation testing, starting from a simple seed program and employing an LLM to rewrite code. Unlike previous methods that rely on existing libraries for mutation, our work does not require such dependencies. While many studies focus on validating functional correctness, fewer have addressed missed optimization opportunities. Our method stands out as it is not language-specific, does not require program instrumentation, and is the first to use machine learning for code generation instead of relying on handcrafted rules.